Section 21.8, Ampere's law. Ampere's law for static magnetic fields is that for any current geometry that produces a magnetic field that isn't changing in time, is static, it's going to follow this law, that the sum of the magnetic field that is parallel to your length segments in the surface that you draw is equal to mu naught, the permeability of free space, times I, where this is a particular I, this is the net current passing through the surface bounded by the path. And the path is defined over on this left side. So here we have two wires, and there's a closed path that's constructed from short segments. The segments are often chosen to be parallel, to have a component of the magnetic field parallel to them to simplify things. And if we want the net current passing through the surface bounded by it, right, so this path is encircling I1 and I2. And I1 and I2 are both in the same direction. So for this example, I is equal to I1 plus I2. And there we have it. Now for this summation, that's easiest to see perhaps with a more specific example. So let's take a look at an example. Example 11, an infinitely long straight current carrying wire. Use Ampere's law to obtain the magnetic field. So we have Ampere's law, sum of the parallel magnetic field components times the short length segments of our arbitrary path are equal to mu naught times I. So if we have an infinitely long straight wire, we could picture that for a moment. If we want to get to our magnetic field equation, how can we derive that result? Well, we know that we have current going up, and so then we can think what shape would be useful. Well, one that's really useful here is if we can be similar to the direction of the magnetic field. If we can go where the magnetic field will go in a circular path around the wire. Why is that? Well, that's now going to be in the same direction as the length. Let's take a look. So since we choose this circular path around the current carrying wire, where at any given point the magnetic field is in the same direction as our little length segment of the path, the magnetic field can be taken outside of this integral and it just becomes the total magnetic field. Then we just have to sum up all of the little paths going around this circle. That sounds like the total distance around a circle, which is also known as the circumference. So if we've drawn a path at radius r, the circumference is just 2 pi times whatever radius we have. Circles are very convenient for the geometries of wires. On the right side, we have our constant mu naught times I, because here the current has just been defined as I. So it'd be whatever this current has, right? We could also add in other currents if there are other currents going up, or subtract them if they are going down. Here it's just I, because we're looking for a general result. So if we divide the 2 pi r to the other side, notice we get the result we had previously gotten for the magnetic field created by a long straight wire. That's equal to mu naught times the amount of current in the wire divided by 2 divided by pi divided by r, which we said was the size of the path, but it's just going to be the distance away from the wire. We could draw that path smaller or bigger and we'd get the same result. So here we've seen how Ampere's law can be used to actually rederive all the results we've already seen. And this concludes chapter 21 on magnetic forces and magnetic fields.